When I consider the entirety of chemistry, of the beautiful rules and laws, of the mathematical precision, of the well-defined structures that arise from a steaming concoction of apparent chaos, one thing becomes clear to me. Inorganic chemistry is most definitely the misunderstood middle child. It doesn't have the hard and fast rules of organic chemistry or the copious calculations of physical chemistry. It is a realm where molecules are uncooperative, and finesse is of the utmost importance. But we humans crave a challenge. The majority of inorganic chemistry deals with coordination compounds. These have metal atoms at the center surrounded by ligands. And ligands are atoms or molecules which have electrons that can donate to the metal center. These ligands can bind one or more times, and usually the more bonds it makes up to a certain point, the more stable the complex will be. For almost a century, inorganic chemistry progressed with the idea that these ligands can only bind to one metal center at a time. But that's the great thing about our universe. There is always more for us to discover. In the 1990s, a Japanese researcher named Makoto Fujita started working with divergent ligands that do not bind to the same metal center. Using these, he made a new type of coordination compound, the molecular self-assembly. And building on that work, he made the very first coordination cage. These molecules can be thought of as molecular capsules, and atoms or molecules can reside inside of these capsules. We can predict which atoms or molecules will enter these, and exploiting this property, we can use them for separations, for isolated reactions, or they can even be used as capsules in biological transport systems. For my project, I'll be using 2 different T-shaped ligands and 2 different metal corners to make a total of 4 different cages. The ligands have 3 binding sites, and the metal corners have 2. So when we set up the self-assembly reaction, we'll be adding a ratio of 2 ligands to 3 metal corners. The exciting part is, one of these ligands has never been made before, and 3 out of the 4 cages will also be novel. One of the ligands is more predictable. It will have 3 90-degree binding angles. But the other ligand is more unpredictable in its binding angles, and will lead to some interesting structures. By using X-ray crystallography, we will be able to see these molecules. This technique passes X-rays through a crystal of the sample, and then we measure how much the X-rays diffract. By taking this data and interpreting it, we can make a model of the molecular structure. Once we have determined we have appropriate cages, by various methods of spectroscopy, we will test them to see what kinds of atoms and molecules would like to reside inside the cage's cavities. Thank you for listening, and I very much look forward to presenting my findings at the conference in March.